for being here. Well, we continue. This is the lecture number 3, okay, of this course. Well, for tomorrow, we are going back to this singular perturbation method to assistant coupling KdV equation with an ODE, okay? So today I have to look at some results about the stability properties for this KdV equation that we're gonna use tomorrow, okay? And well, they have, of course, their own interests that learning some different methods for stabilization, okay? So that's the plan for today and for tomorrow, okay? So I have 2 hours today, or just 1 hour, right? But we were very happy of hearing Jean-Pierre, so nobody say nothing, no? We were all happy. So, well, for today, so we're yesterday we looked at the second part of the lecture to this KdV equation, okay, where we put an internal control. We see that it dissipates energy, and we study the long-time behavior of the system. We finally, at the end, put a saturation term, and we see that everything was working well, okay? Now we're considering the same equation where the linear and the nonlinear one, okay? But now we will put a control term acting on the boundary, okay? As we saw yesterday, for this equation, we have to consider 3 boundary conditions, okay? 1 on the left and 2 on the right, okay? And we are considering, so the control acting on the left, okay? So on the Dirichlet boundary condition at x equals to 0. This is the operator K that we're gonna build, okay? Well, we will use as on the first lecture for the wave equation, the backstepping method, but here I'm gonna show you a little bit more details on the existence, how we prove the existence of this transformation that relates the original system to a target one, which has these good properties concerning stability. Okay, so here we have, which is a paper with Jean-Michel Coron, and we have 2 results for the linear and the nonlinear part, but here again, as Jean-Pierre mentioned, and then for a question about nonlinearities, is, let's say like that, an easy nonlinear result, because it's just a perturbation of the linear case, okay? So we just put a smallness condition on the initial data in order to have the result for the nonlinear system, okay? So we're gonna, for any decay rate omega, okay, we are gonna build a feedback law, this operator K, okay, such that the energy of the system, del 2 energy of the solution, okay, is decreasing exponentially to 0, okay, for the linear system, and then for the nonlinear system, and there for the nonlinear system, we add this parameter R, bounding where the initial data can live, okay? So here, in both cases, in fact, we found the same control. Well, in fact, we use the linear control in the nonlinear case, okay? And the control is given by the backstepping method, so it looks like that. So K of U is going to be given by the integral between 0 and L of a kernel function, okay, K times the solution U. So here we're going to get these results where what is called the full state feedback, okay? So in order to compute what control you're applying at time t, you need to know the solution in the whole domain for that particular time t. Okay, so that's called a full state feedback. Okay, we'll see that this kernel K, as for the wave equation that we saw on Friday, okay, in lecture number 1, is going to be by a solution of a new differential equation. Okay, and yeah, the last line said that in fact we are not able here to find a closed formula as for the wave equation in some cases for the KdV equation. So we just work with this system and we characterize the solution. Okay, but we are not able to identify a known function in order to write a closed formula as for the wave equation. Okay, so the linear system, okay, in order to do our control design, we have the linear system 21, okay, and we fix omega, so the decay rate that we decide for the system, and we look for a transformation pi, okay, defined in that way, going from U, which is solution of the original system, okay, to some V, and here we see that, in fact, what we want is to relate the solution of our original equation to this one, where we have the same boundary conditions, we have homogeneous data, okay, and the key part is that we add this term omega V, okay? Omega is a constant, okay, and this internal term V, okay? So it's very easy to see that this system, when omega is constant and has the good sign, has its energy is decreasing exponentially to 0, okay? That was related to the internal control that we saw yesterday, okay? In fact, yesterday we considered a function omega of x that has may have some compact support, for instance, included in the domain. Here is just a constant because this is not the original system. That is what we want to use in order to get the stability. Okay. Well, we look at this what we call the target system for V. Of course, we can do as yesterday the same computation. Here we have the derivative of this energy, okay? We found again this trace Vx at x equal to 0, and we obtain the internal term. And because this omega is constant, we get the full energy with the right sign, okay? And in fact, in this case, with this internal damping that we add, we can just neglect the boundary trace that was in fact the main concern in that situation. But here we just forget about it and we keep this minus 2 times omega the energy. Okay, it's a very simple computation to get that. And so we have that V dot is less than minus 2 times omega times V. Well, V is energy function for the solution. Okay, so we get the exponential decay of the solution. Okay, very nice, easily to get. So the target system is a good one. Okay, has the good properties that we're looking for. So, well, here we can see this parenthesis if this decay rate is sharp or not. Okay, because we know here we have 2 terms, we are neglecting this trace, okay? So we can see if the system has the good decay rate or not, okay? So this here, we don't have, for instance, for the space operator, we don't have a basis of the space composed by eigenfunctions, okay? That's a problem in different situations. So here, doing the computation of eigenvalues, eigenfunctions, so tell you some particular behavior of the solution for some initial data, okay? But you cannot characterize all the solutions, all the behavior of the solution by doing this spectral analysis. But anyway, we can do it here. In fact, we are just showing some numerical computation to see what's going on in this system, okay? So we're interested in that system, okay? So because the term in omega is just is multiplying V, so the eigenvalues of the system up there are the eigenvalues of the system in the middle, but shifted by omega. Okay, that's very easy to obtain. So we can just take a look first to this system where there is no omega, and we know that for different values of omega, the eigenvalues are just shifted by omega. Okay, so these are the eigenvalues. And here, we are just to have a feeling, we can compute numerically what is the situation of the eigenvalues. Okay, and here, what I put surprisingly, but it's not that such a surprise, in the sense that we know that the behavior of this system depends a lot on the domain where you are working. Okay, saw it, and in fact in the lecture by Jean-Michel Corona, also you saw it that there are some critical values. We talk about a little bit about that in these lectures. Okay, so here, for instance, this is the case L equals to 1. Okay, so it is not critical. So we know that the system is exponentially stable. Okay, and well, this is numerical development for some simulations. So the first eigenvalue, okay, we see it here very near from 0, but you know, look at the scale. So in fact, it's very far. It's minus 72. Okay, for the domain 0, 1, it's minus 72. So we recovered that the system is exponentially stable even without considering the term omega. Okay, we proved that yesterday. Okay, so here there is another. This is the first one critical value. So we consider here L equal to 2 pi, and we know we can prove now that the solution 1 minus cosinus x is the solution conserving the energy. So okay, and here we recover that and see that in fact sigma 1, the first eigenvalue, is just 0. Okay, and here you see that you really need, in order to get the stability, you really need the term with omega in order to shift the eigenvalues to the right side. Okay, of course there are situations, for instance here, L equal to 2 pi square root of 7 over 3. Okay, here you find numerically these two eigenvalues. Okay, minus 0.2, okay, and the positive 1, okay. You know, here we have that there appear more than one solution that conserve the energy, okay. And so you can see here, and here again, you see that in these critical values, in order to have this stable system, you really need to consider the parameter omega, okay. And with omega, you can move the eigenvalues, or you can put the energy going to 0 as you want, okay? Well, we know that without doing any numerical simulation. We know that from here, okay? So in the critical cases, this trace term is not useful, okay? But in the non-critical cases, that is the term that gives us the decay of the energy without omega, okay? That was just to feel a little bit what the situation for the stability with some numerical simulation. So go back to the problem of finding this transformation. Okay, we want to find this transformation from the original KdV equation to this target system with the term omega, okay, in the interior. Well, I put the computation because then you can get the slides on the website, so we are not doing the computations here, okay? But just a little bit, okay, just to show how it's going. So you want to recover what is the equation satisfied by V. So you start computing, no? Vt equals to ut minus, you derivate the integral term with respect to time, okay? You get ut in the interior of the integral in blue, and you use the equation, and then you integrate by parts, okay? That's the methodology, and you get many terms, okay? Many terms, and then you have to do something with them. We're gonna see what means something, okay? This is for VT. We can do, again, the same for Vx. Okay, here, of course, as the integral depends, it goes from x to L, you have to be careful to integrate, to derivate that, okay? But you obtain easily some terms for Vx, okay? For Vxx, for Vxxx, okay? In all these cases, you obtain some integral term and some point terms, okay? And then you have to put all together and see which are the conditions on K, on the different terms with K, to see that when you compute Vt plus Vx, Vxxx plus omega V is equal to 0, okay? So there are very easily computations. It's nothing strange. Okay, you just have to track all the terms and put them together. Okay. So here, so in blue, we rewrite the equation for V. Okay, the corresponding KdV with this interior damping term. Okay, and we obtain all those terms. Okay, we put it together, and we have here, for instance. We have the integral term, okay? We want all that being 0, okay? We want to kill the integral term, so we get, imposing that all this is 0, we will get an equation for K, okay? And so here we have, for instance, Uxx at L. So we have no information about Uxx, so we really need to impose that K at XL is 0, okay? And the same with the other guys. So here we have to impose that this term is 0 and that this term is 0, okay? So doing that, here is the domain, or the kernel K is defined, okay? Because the transformation for K is in a triangular domain, okay? Here, X goes from 0 to L, and Y go from X to L, okay? Because of that's what you need in order to do all your computations. So that's the domain that we call capital Tau here, okay? So we just put together all the equations that K has to satisfy, and we obtain this in the box, okay? So we have an equation inside the triangular domain, and we have 3 boundary data, okay? We have 2 of them in the diagonal, okay? And the other one with the second variable is L, so on the top. So we have 1 boundary condition on the top and 2 on the boundary, okay? In order to see in a better way how to prove that there exists some solution to this kernel equation, okay, we just do this change of variable, okay? We go from x, y to tx, okay? Well, the new kernel, we call it G here, okay? We have, of course, this relationship between K and G, okay? And we start computing all the terms in order to write the equation not for K, but for G, okay? And doing that, well, the domain change, of course, now is this new triangular domain here, okay? And this is the equation for G, okay? Now we have a GTTS plus GSSS plus GS with some factors, okay? We can think where are these 3 boundary conditions now, okay? For instance, the last 2, okay, are here on the bottom. Yeah, the last 2 are here on the bottom because S S0, okay? I put x, y there, but there are the new variables, here, S and T. So for t equal to 0, here we are here in the bottom line, within between 0 and 4. This is a design when capital L is 2, okay? And the other one here is on the second diagonal, okay? Diagonal going down, let's say like that, okay? Here. And so here we will, in fact, obtain the following. I will just show you the following integral equation, or differential integral equation for G. So in order to get that, we have to write G in terms of the other things. Okay? And so we have to get a formula for G, was also depending on G inside the integral. Okay? But how we can do that? We go back here, so we take this one, the first term, this 6 times G TTS. Okay? And so in the next slides, I am describing how you have to integrate in order to obtain this. Okay? But instead of reading that, maybe it's a good idea to do in the following way. So for instance, when you are in any point of the domain, okay, in order to integrate and get something, you have to, for instance, remember, you have two kind of information on the bottom line, and one on the second diagonal here. Okay, so when you are in a point here, you can integrate once vertically on time. You can also integrate in a second time integral vertically on time, on t, it's not time, it's t, and then you can integrate once on s. Why you can do that? Because you have two boundary conditions here and one boundary condition there. Okay, so what is nice is that here you obtain this, you have this term GTTS. So you can take this one, write in all this integration, and obtain the following equation here. Okay, so we write the equation in variables n eta c, we integrate, and we are using the boundary condition. In the slides, I describe how you can use the different boundary condition in order to get this. How is the order, the way to integrate with respect to each variable. Okay, so we obtain this one. Okay, and this one has the well, a different form, is equivalent to the other one, but what is nice is here the following approach works. Okay, and this approach is using the method of successive approximations. Okay, so what does it mean? Well, in fact, it was the same approach than for the wave equation. Okay, the difference that for the wave equation, in the case of constant coefficients, once we have the formula that we're getting here, you are able to identify some already known functions in order to write a closed formula. Okay, but even for the wave equation with non-constant coefficient, you are not getting a closed formula, you are getting just a series, a convergent series in order to define your kernel function. Okay, so this is a recursive way to get the solution. So you just start guessing that the function is, this term comes from, let me go back 1 second, from the term here without integrals. Okay, for instance, you start saying that this, and then you update your guessing using the integral part. Okay, so you start with G1 in this way, and then Gn plus 1 is the integral part of your formula depending on the previous G, on Gn. Okay, you define this method like that, and for instance, well, you can get tired doing some computations, okay, in order to get G2, G3. At that time, I did some of them, okay, just in order to see what's going on, okay. But the nice thing that you can finally write a formula with good properties for the coefficients of this series, okay. Okay. So Here, the important thing is that, you can bound this GK. Remember that you were trying to prove that the G, written as the series of all the G's, is your solution, okay? So for any of these G, you can find this formula, okay? And rather than that, you can prove that these coefficients have this, look like this, okay? So have some good converging properties in order to continue looking at that, okay? So, well, of course, the nice implication is that the series of this GM function is uniformly convergent in your domain, okay? Well, that gives us a solution because now if we define G as the series of all of these Gn, okay? In fact, for instance, here you start from G, you do like that. You consider this G1 plus G1 here, and here Gn plus 1 is the formula of all this n. And using that all the series are convergent, you can in fact exchange the integral with the series, okay? And recover inside the integral finally again this G function. This function named G, okay? So in fact here we can see that this G is equal to this thing, and G1 was the term outside the integral, which is not depending on G. So this is exactly the formula that we wanted to get, okay? So here I'm just again doing some numerical simulation to feel again how is this kernel function, okay? For instance, I am doing this for different values of the domain. Remember that for some domain, it's very easy to stabilize when the domain is not critical. When the domain is critical, it's harder to stabilize, okay? So this numerical simulation is just to illustrate that fact. For instance, here, for L equals to 1, so it's not critical, so it's very easy to stabilize because the system is already stable, okay, without doing nothing, okay? So here we can see that, of course, this is a function who looks like this, but the values are very small, so it's kind of a flat function near to 0, okay? When we do the same, but for instance, for a critical value, L equal to 2 pi, well, the shape is kind of similar, okay? But here what is important to look is at the scale here, okay? So here is like a flat kernel, and here in the first critical case, L equal to 2 pi, okay? We see that here we need some power. Okay, we see a solution, okay, which is not flat equal to 0, very near to 0, that's now is different, okay? And for instance, in the other case where we have more than one function, which is conserving the energy, we have here 2, we see that, well, the shape again is kind of similar, but the scale, so the power that you need is becoming higher and higher. Okay, that's a numerical simulation just to feel that theoretical result that we have. Okay. Well, so in order to get the stability, we need a transformation going from the original system to the target one, and we also need the inverse transformation. Okay, or one transformation going in the other sense. So you can do again all the computations in order to have a formula for the inverse transformation. And well, again here you get a system for a kernel of the inverse transformation, okay? And well, this is the inverse transformation going from V to U, okay? With this kernel L, okay? So the method to prove this L and to get this L in hand is the same as before, okay? And so, well, you have this operator pi, or capital Pi, okay? which is the transformation from L2 to L2, which is continuous, okay? And so we have this constant decay relating the norm of f and pi of f, okay? And of course, we have the same for the inverse map pi minus 1, okay? It's also continuous, and we get the existence of some constant dl, okay? So, well, now you have all the ingredients to prove the stabilization of the system. So we start with some initial condition U0 for the original linear KdV equation, okay? You transform and you get V0, which is pi of U0, okay, using this transformation. When you are in V, you have this nice exponential decreasing to 0 in the variable V for the system, for the target system, okay? And then you have to going back to U, okay, to the solution U, not to you yourself, okay? And so you use here the constant dl and the constant decay in order to put on the left-hand side your solution U, and on the right-hand side the norm of the initial data U0, okay? So here, so this just find at the end of the day, you get the solution of your original system is more than a constant, and this exponential decreasing function with decay rate omega. Okay, so now again, this is for the nonlinear system. Also, yesterday we saw how to deal with some nonlinear perturbation. We're using the energy, okay, and how there are some garbage term appearing, and how you can absorb them with the good part of the Lyapunov function, okay. Here is kind of we're doing the same. So now we apply the same transformation, but for the nonlinear equation. So we get the same as before, plus some term coming from the nonlinear part, okay? Which is, well, this one, okay? Remember that is kind of Vx, okay? Or this is coming from Ux, in fact, okay? From Ux, that's the nonlinearity. And of course, with the same homogeneous boundary condition as before, okay? So here again, we're just taking a look into how to do this computation. So we obtain the derivative of the energy. So we have, as before, this term coming here. We have the term coming from the interior damping term, okay? And we get this extra term coming from the nonlinearity, V times F, where F is this guy here, okay? Coming from the nonlinearity. And so how we can do that? Well, we do some estimations, and this term, which is we already call that kind of term as a garbage term in order to these perturbation arguments, okay? So this guy, which is this guy, can be bounded in this way, okay? Okay, that's the way that you can prove. So we have here a power, the energy of V to the power 3/2, okay? And so you can really see what kind of initial condition, smallness condition for the initial data you have to impose in order to get an estimate for the time evolution of the nonlinear system, okay? Once you impose some smallness condition on the initial data, okay, you obtain, as before, this formula giving you the exponential decay of the solution, okay? So this is the theorem that we wrote at the first slide of this lecture, okay? So I put it again just to recall you the result, okay? For any parameter omega, we were able to build this feedback operator K, okay, which here is depending on the solution in the whole domain, okay? And we obtain the decay rate for the solutions. So what we have done, we apply the backstepping method in order to stabilize from the boundary this system. Okay. And well, the closed system is proven to be locally exponentially stable. Okay, that's a summary of what we have done in these previous slides. Okay, so let me do some comments about what happens if you want to apply this method, but when you put some control not on the left-hand side of your interval, but on the right-hand side of the interval. Okay, on the right-hand side you have two boundary controls. Okay, so you can even play with two guys, but as this backstepping method is defined by finding some transformation on the system here, where in fact these two control K1 and K2 will be given by the transformation. So you don't see a much more degree of freedom when you are dealing with this backstepping method with more than one control boundary, at least boundary, acting on the boundary. Okay. So some details, well, so we have to impose, of course, when we do the backstepping computations, we have to impose this equation in red, okay? That V is solution of the Wood target equation. And as before, we get some terms. Well, there are more than that, but at least we have this term here, okay? As we don't have, as previously, this uxx at x equal to L, so we have to kill it. We have to kill this term. We don't have possibility of playing with that. Okay, so we have to impose that condition. And in fact, in order to get this homogeneous boundary condition for our system, we have to impose other condition on K. Okay, and we see that we get 4 boundary conditions to kill or to impose on your kernel equation. Okay, but your kernel equation are defined on this triangular domain. So, and if you remember, there are the same number of derivatives than for the original equation. So, for the kernel K, you get some terms K xxx minus K yyy. So, there is derivatives of order 3 in your kernel equations. Okay, so when you start imposing more than 3 boundary conditions, it could become overdetermined. Okay, so that's a problem. In order to do the same approach than the one that we did for in the situation where the controls are on the right. Okay, so then you can say, well, but in order to define our feedback control, let me go back a little bit to the way here. Well, no, for the transformation. Yeah, we use some integral from x to L. Maybe if we change the position of the control, we have to not integrate in between x and L, but between 0 and x, as is the case, for instance, for the wave and for the heat and for many equations that both kind of transformation works well, okay? But again, you will face some trouble when you do that. In fact, well, that's the idea. Natural idea is to change where you are integrating your transformation, okay? But again, which is we can find here the details, okay? But again, what's going on is that you get so many terms to cancel, okay? More than 3, 4, or more, okay? So you don't expect that just changing the interval of integration, or you can manage all these garbage terms appearing in your kernel equation, okay? And of course, we know that if we were able to do something from the right, we have to be careful because we know that in some situations there are critical values, okay? So in such situation, it's not able, you're not able to stabilize because you cannot influence the evolution of your system acting, for instance, on some boundary on the Neumann boundary condition from the right. Okay, so if some approach like this work, you have to recover the situation that that approach can work for some L, but you have to be able to see that this approach is not working for the critical length L. Okay, so it's a warning that is a very hard problem in order to do a backstreet information like that. But in a paper by Corona Lu, they don't care about trouble, so they just go inside and prove that, in fact, not using this kind of Volterra transformation, but using, instead of that, I didn't write the formula, but instead of doing this kind of transformation, they just integrate between 0 and L on the whole domain at once, okay? And what's happening in that situation is that, well, they are able to get the results, but in fact, the computation are very hard. The analysis is very hard to perform because the kernel equation, because differential equation in your, now it's not a triangular domain, but it's just a square, but with a system like a delta in the diagonal, okay? So that makes much harder the system to study, okay? That's one of the difficulties, but Corona Lu did it, okay? So that is a very nice paper and very hard, okay? Well, now I will tell you, I have 30 minutes. Yes, okay. Now, we know today for the boundary, we put a control on the boundary, but the feedback control depends on the whole solution, okay? So now the question is, can we do the same, but with a control depending only on some part of the solution, okay? Or here, are we able to get a result just measuring for each time t some boundary condition, some boundary data of the solution, okay? So here there are a general approach, but well, the goal is to design this controller, okay? And the idea is that hopefully we get a feedback control law depending on only some boundary measurements of the solution, okay? It's like what Emmanuel mentioned that in yesterday is when you have your system. This is the in Rn, okay? Yeah, when the system is controllable, okay, you know how to build this U in the form K of X, okay? This is the usual full state feedback, okay? That's what we have done here, more or less, okay? And so what we want to do now is, okay, can we do that, but with a U not depending on the entire X, but just depending on some output of the system, so which the output is given, for instance, here, a certain matrix C times the full state, okay? And so to do that, you need the concept that Emmanuel reviewed yesterday of observability, okay? Can you observe the system? So under two conditions, the controllability of the system, okay, which depend on the matrices A and B, and the observability of the system depending on the matrices A and C. In finite dimension, you can always, under these two conditions, you can always build this control depending only on the output, okay? Yeah, and in order to do that, you have to build, in fact, you are not able to do that with a static feedback, but you have to do it with a dynamic feedback depending on an observer, okay? Which is mimicking the dynamic, the original dynamic of your system, okay? So in order to do that, you have to build an observer, okay, such that you have this convergence, okay, when time goes to infinity, of course, okay, and where there is a very classical method that we're using here, that this is the Leuenberger observer, okay, telling you how to get this observer, okay, and at the end of the day, instead of putting a control depending on kx, you consider a control depending on the observer, x dot. And in fact, what you have to your disposal in order to build this observer, y. Okay, so you can do this approach in order to obtain this first an observer and then a whole system where your control depends on the state of the observer, and the state of the observer depends on your measurement y. Okay? So this is what we're doing here. Okay? We have a minute. Okay, yeah, here, for instance, well, you know, the one, well, I said natural, but well, a natural choice for the KDV equation should be considered these measurements, y, as one of the boundary conditions that you get in the computation. Boundary data that you get in the computation. So, for instance, here, y of t could be yx at 0. But because of the existence of these critical values, it's not going to work because the condition on the observability of your system is not going to be satisfied. Okay? So you know that the system is not observable from that quantity. Okay? You have the evolution of the linear equation. If you just see this output here and you see that it's 0 for any time, you may guess the solution is 0 for any time, but it's not true. We know that. Okay? So first, we consider, instead of this, we consider these other measurements, okay? Y, x, x, etc. And we were able to build this observer and prove that the system is going to 0 with a feedback depending on that y, or that output y, okay? So first, of course, we need a lemma, okay? Because we always have to worry when dealing with PD with the regularity of the solution, the existence, and the link between the regularity of the data, of the boundary conditions, okay? But here, well, you know, we have to work, instead of working in L2, because of this term UXX on the boundary, we have to work in H3 for the state of the solution, okay? So here again, and the method, we can again use the backstepping method in order to build the observer. Okay, we're not going into the details, but you can build that in order to, you can use the backstepping method in order to build your observer, okay? And it's again given by a kernel transformation like this one, with some kernel function P, okay? I just put P here, but you can find the right P, function P, okay, but as the solution of some kernel equation as before for the kernel K, okay? And just going quickly through this, okay? So by following a classical approach, that is the Leuenberger method, in order to build this observer, okay, we can construct this system 22, okay, which is U hat. For U hat, and U hat is like X hat here is the variable that is approaching the original state, okay? And so here we have in black the KdV equation, okay, and we have an internal extra term here. This P coming from the kernel, and we have here Y, so is Uxx at x equal to L minus this other quantity, but depending on the observer. So the observer is you build it, so there is no problem that is there, okay? So we were able with some marks to prove that all this works. That means that we can prove, well, here I miss, here instead of U is U minus U hat, okay? Well, here, instead of U hat is U minus U hat, so you can prove that U and U hat are converging to the same point, or to the same trajectory, okay? And here, you know, there are two things. There are the control and there are the observer, okay? They both are built with this backstepping method. The control K is the same as we used before, okay? But we are not putting K of the original solution, but we are putting K or kappa of the observer as there, as here, no? Your control is not anymore depending on X, but your control is depending on the observer X hat, okay? And you can prove that the system is behaving like this. So we have exponential decay to 0 of the solution, and that the observer is exponentially approaching the trajectory U. Well, this is the way, no? Here the control kappa, okay? The control kappa is the one we just built, but not for U, but for U hat, okay? And we transfer the system, okay, to another one which is asymptotically stable, okay? That's the way that we can prove that. In fact, we define a new solution, okay, U tilde, which is U minus U hat, and you keep U hat, and you can do now a backstepping transformation using two different transformations, okay? And you get this system, and you can study that this system is exponentially stable, okay? Well, and to prove the exponential stability, here we need a Lyapunov function, which is not that nice because that imposes all this regularity framework in order to do the computations, okay? We have here W tilde XXX, okay? We need it because we have in the computation of course, we have this kind of trace, the second derivative of one of the solution on the boundary, okay? So in order to manage all the computation, we need this Lyapunov function, okay? And for that, we are able to prove that the system is exponentially decreasing to 0, okay? Here, so this is the result, okay? So for any parameter omega, we can find, well, there exists some constant such that for any initial data now in H3, okay, the solution of, and here we have the system, where is the same system where in blue is just a control. It's just a control, not just a control, but it's the control, okay? In blue is the control depending on U hat. And so you need U hat. And U hat is given by the second equation, okay? Depending on this P, so this is a given function now, this K is a given function, and so the red term here is the output that you can measure from the inner system, okay? So now your control only depends on this red term, Uxx at x equal to L, okay? And we can prove that all this is going to 0 in an exponential way, okay? So here, well, we do some numerical simulations just to illustrate the results. I'm just keeping that to say a few words for ending, okay? Well, here in this paper with this output UXX at x equal to L, we were not able to do the nonlinear case, okay, because of regularity issues, okay. The output is too weak, okay, in order to do the computations. Of course, there are other results. Very out of time, but here, in fact, with other boundary conditions, we were able to do the same with, again, with some marks, okay, from France. We were able to do the same, but here the output and, in fact, the boundary conditions are different, okay? So we have the Dirichlet boundary condition on the left, where the control is acting, but on the right, we change the boundary conditions, okay? Instead of putting U and UX, we put UX and UXX, okay? And so now, the quantity U at x equal to L is free to measure. It's not part of the boundary conditions, okay? And so we measure U, and so we build this observer depending on U at x equal to L, and we are able to prove the same result as before for the linear system and for the nonlinear system, adding, of course, a smallness condition on the initial data, okay? That was only to get rid of these regularity difficulties coming from the very weak regularity of the output that we had previously, okay? And here there is another observer that will be useful for us tomorrow, okay? Is that this is a paper by Balogun, Marx, and Astolfi, okay? That here they really need being in a non-critical case. Why? Because in his observer here, they are measuring the quantity that we know that is not observable. The system is not observable with these measurements when the domain is critical. We have already seen that several times, okay? So here they need a non-critical domain in order to get some information from that trace UX at x equal to 0, okay? And other things are the same. Of course, the kernel K and P are changing from one slide to another, okay? They are different, but very similar, okay? Okay, thank you. That's what I want to tell you today. Thank you very much.
So thank you, Eduardo, for the nice talk. So if you have questions, you can ask Eduardo. Also, if there is a question in the online, they can ask.
So maybe, yeah, technical question about the convergence of the observer towards the state U. In one slide, I think 126, in your result with Marx 2014. Yeah, yeah, this, not this one, but after. So here you have the exponential decay rate for the observer in L2, and U is in H3.
Ah, okay.
Yeah.
But this is, yeah, this is the linear case.
Yeah. But after, you have another estimate with U minus U hat, 2 or 3 slides after.
Yeah, yeah,
in H3.
Yeah, I changed one and not the other one. Yeah.
And
I made a mistake when I put the, yeah.
Okay, so finally my question is, U hat is in L2 or H3, the estimate of U hat?
Yeah, and
because if you go to slide after,
yeah,
here, so if the difference converge in H3, and U is also in H3, so necessarily U hat is in H3.
you had in stage 3.
Which is strange. No, I don't know.
Yeah. Let me check this. Because for you, we really need H3. Okay.
Yeah.
For you, we need H3.
Yeah.
That's for sure. For you had L2 is gonna be fine because when you are in H3, this trace is a continuous function.
Yeah, sure.
So for U hat, you don't have this regularity issue for U hat.
Yeah, but if you, due to the triangle inequality, if U minus U hat is in H3 and U in H3, there is something strange, no?
Yeah, no. In fact, there are also the U hat XX on the second equations. Yeah. No, I think that made a mistake when I put the
yeah, okay.
this.
Yeah, I think maybe it's L2.
Yeah.
Yeah. Thank you.
I will correct it for the version on the website.
Mm-hmm.
Thank you.
Thank you.
So is there any other question?
Yes, thank you. Yes, I have a question related also to your second lecture. So is there any result about the global stabilization of KDV?
Global?
Yes, is there any result?
Yeah, well, there are different results for global. Well, the first one is kind of what I mentioned yesterday is kind of semi-global.
Yes.
Okay, and then there are other feedback built by Rossier with Camille Laurent also and Bin Yuzhang,
Okay.
dealing with obtaining some really global results.
Okay. Okay, thank you. Thank you.
So that is for the non-critical case.
No, but then in those cases there are internal controls, so you don't care about the critical case.
Because in critical case, you told something like a 1 by root to the power half, some kind of stability will be there.
In case of
Critical case, there is some stability of 1 by t to the power half.
it's as mentioned by Chu Chang and Coron, and also in Nguyen with some, but you get asymptotical stability. Okay, asymptotical stability using the nonlinearity.
Thank you.
I have to.
Is there any other question? Okay, then thanks, Eduardo, again.
Thank you.